let's figure out. We covered static routing. Okay, so AD and metrics. Okay, so administrative distance. All right, let's go back to our. Looks like here, and let's take a look at our routing table. Okay, now the routers are not running. Okay, all right, so we're just gonna go back to some previous output. Okay, so we have an administrative distance and a metric. Okay, all right, so let's take a look at this here. Okay, now remember, our administrative distance for connected interfaces is 0. But, okay, we have a static entry here. Okay, all right. But this is, where is our, okay, let's go back up and let's see. Oh, we ate up the filter. Okay, let's go back up here. We might turn the damn radar on. Okay, wow. Okay. I guess we're stuck on turning this bad boy on, so I'm sorry about the noise. Okay, while waiting for those to boot, let's go back and talk about our stuff here. Now, every routing protocol, which we have not configured yet. We have not gone through routing protocols, okay, and but we've done static routing so far, okay, and we've also talked about the overhead on when you need to make sure, and will you see static routing to that degree where routing protocols are not being utilized? Yes. Okay, depending on what security type of parameters are put in place for that company. Okay, some believe that routing protocols are a possibility of being altered by hackers and things of that nature. So everything must go in and out of the data center via static routing. Okay, yeah, that's a pain. All right, and makes you really pay attention to detail. Okay, and I worked, and okay, so working for a company for 5 years, 10 years straight. Okay, you as a network engineer are limited to that particular network. Okay, and what you see as law is not the norm in a lot of cases. Okay, now as a contractor and a consultant, okay, that's a whole different ball game. Okay, and it takes a certain type of temperament to deal with that. Okay, all right. First of all, your contract can end at any time, especially at an at-will state. All right, at-will means we can get rid of you because we don't even like your hair. All right, your hair color. We're not going to tell you that. We're just going to let you go. We don't have to give you a reason. Okay, so your employment of 12 months out of the year is not really solidified in a lot of ways. Okay, but if you're in a state that is known for that, okay, your resume looking, 3 months, 6 months, 1 year contracts, okay, and you can't find a position that's over a year, okay, or even 3 months, they don't care. Okay, they know what their state is like. Okay, so I have in the tri-state area, Maryland, DC, and Virginia. Okay, they're all at-will states. Okay, and nobody cares about the short-term jobs that I have because of contracts. Okay, They're not full-time employment. They're contracts. Okay, now, once in a while you'll get someone that will question it, and it's like, obviously, okay, you don't know what you're talking about. Okay, now that's not what you're going to say to them, but these are recruiters. Okay, keep that in mind. All right, a lot of times you have to, if you are have the temperament, you need to educate these recruiters so they can help you get a position and explain to them that, hey, this is the norm. Okay, all right. That's just the way it is. Someone like Northrop Grumman that comes by, they'll understand why your job history is 3 months, 6 months, 1 year. Okay, it's just the way it is. And do not tell me that you cannot build a great resume from those stats, because I have. All right, so I'm a walking proof that this is not a reason for you not to find work. All right, okay. So now, let's get into here. Okay, show up your route. Is this thing not saving my? No, it saved it. Show IP interface brief. Okay, that's up. And that's up. Oh, I guess I didn't save it from my include IP route. Nope, it didn't save it. Okay, so it didn't even save my loopbacks. Okay, so IP route. Okay, so it doesn't matter that I don't have a loopback over here. With that, it's still going to go in the routing table. Okay, we put it in there. Okay, all right. So now, okay. Okay, all right. We have a metric of 0. Okay, because it's directly connected, right? Okay, all right. We got a distance of 1 because it's a static route. So the distance is your administrative distance for a route. Now, okay, if this was another method, which you'll see in the future, you're going to have the administrative distance of 110, 90, whatever the standard of that routing protocol is. And your distance can be changed manually. Keep in mind, you have full control of this as an engineer and as an administrator. Okay, these are managed switches. Okay, meaning an unmanaged switch is going to be something, or an unmanaged router, it's going to be a crappy piece of crap that you get from Verizon. They're Files routers. Okay, all right, those are unmanaged. That doesn't mean you can't log in there and do things, but there's some things you cannot stop. Okay, all right. If you want to have full control of your network, all right, you need to bypass that router. Okay, by using a DMZ, okay, and flow that traffic into your router. Okay, now here's the thing. Okay, your metric is the measurement of your route. Meaning, I'm going to give the route a measurement, which literally means just a value based on numbers, okay, to tell you what route is there and what distance it is to get to that route. Now, EIGRP has its own method of doing that, but you can manipulate that by making changes to make your metric lower. So if I have a router that is learning 2.2.2.2, okay, from 2 interfaces, okay, all right, and they have the same metric, okay, they can both go into the routing table, okay, and we can share the load by going across multiple interfaces. But if I want to take one particular route, meaning that I want to choose FA00 to be the primary and FA01 to be the secondary, I change the metric on FA000 to a lower metric. Okay? Now, what is a default route? Remember we talked about before with a PC. TCP/IP will send traffic to its destination anytime it is in its own network, its own broadcast domain. And the cool thing about it is it will propagate the ARP table. However, anything outside its network, okay, it has to be sent to the default gateway. Now, if you don't have a default gateway configured, okay, guess what? Sorry, I lost a little bit of time there. When I mean lost time, I'm like spacing out. Okay, all right. Let me catch up to what I was saying. If you do not assign a default gateway, okay, your traffic goes nowhere. Anytime you try to ping outside the network, it goes nowhere because it doesn't know where to send it. So that's why the default gateway is important. Okay, you will receive a default gateway on your PC by either manually putting it on there or DHCP. Okay, which here's my default gateway. Okay, all right. So now, okay, sorry about that. I was really distracted there for a moment. Okay, so now, all right, we understand what our metrics are, and we understand our administrative distance. Now, okay, these two things are there. So the administrative distance is there as a tiebreaker to say, hey, I got multiple routes coming in from multiple sources. Okay, all right, which would be routing protocol, static routes, whatever. Okay, and the administration distance makes the tiebreaker, okay, of which route goes in the routing table. All right, like I said, EIGRP, administrative distance of 90, OSPF 110. EIGRP is going to win every time until I change either OSPF distance to lower to 90, okay, or EIGRP over 110, okay. All right, now these are default values. I can make EIGRP number 2. As a matter of fact, I can make it 1 as a static route. Okay, all right. It doesn't really matter now. Okay, that is the administrative distance as a tiebreaker to what goes into the actual routing table. All right, when multiple paths are actually learned for a destination. Now, metric is your distance of how to get to that route. How far is it from me? Okay, and every router is going to have a different distance. Okay, based on, because they're separate entity. All right, now you're starting to understand why I want you to see it as such. All right, because one router has nothing to do with the other router. Yes, they will send their information to another router. That router will actually add value to their metrics on top of the metrics that was given to them, right? Because when router 2 gets a route from router 1 is going to say, hey, this is 3 hops away, or this has a metric of 200. Okay, so router 2 is going to say, okay, well, I'm going to take your 200 and put 100 on there. Now my metric for that route, from router 2's perspective, is 300. Did I say 200 before? I can't remember. All right, now, okay, so that's how that works. All right, you can look at them communicating with each other, or you can look at it, which I would like you to do it this way, okay, which I'm about to explain, and that is looking at a router from the perspective of, hold on, my mouth is getting itchy. Oh, that means I need to stop talking so hard. So now, okay. Router 2 is going to get information from router 1 about a particular route. Okay? Router 2 will respond locally to its own router to add metric, distance, whatever it needs to. Now, not administrative distance. The administrative distance is based on its calculations. Okay, whatever routing protocol you're running or however that router is set up. Okay, that's why you need to look at them separately. Okay, yes, it is based on the information that they receive, but their routes in their routing table is their own. Okay, all right. And if you look at router 1 and 2 as a complete entity, okay, you're going to miss some fundamental aspects of how this information is retrieved. Okay, and you're looking at it as a whole instead of looking at it as little separate bits of entities. Okay, meaning that everyone, yes, you can look at it as a whole domain. Okay, but it's the whole domain exists by each separate component, which will be router or switch in that domain. Okay, so during a troubleshooting aspect, think about it. Okay, when you're looking at router 2, say, okay, so router 2 is getting this information from router 1. Okay, all right, let's look at the information that it got. I see that. Okay, oh, I see why it set this metric for there. Okay, but, okay, somehow if it goes down this interface, it's a broken link. So let's go ahead and change the metric to switch it over to this one, and your traffic works. Okay, now that's a very vague and poor analogy, but still, it's the beginning. Okay, so in the beginning you're going to get a lot of poor stuff until we start building those blocks to get you to more specific things to make the light bulb go off. Okay, so our default route is, which we're going to demonstrate here, okay, is something that is a means of saying, look, when you are routing to something that I don't have in my table, okay, the last step that we're going to take is use the default route. Okay, all right, so now let's do that. So show IP interface brief. Okay, and we're going to actually take out include IP route. Okay, and we're going to say no. All right, and select this. Jesus. Come on. Alright, you know what? This is being a pain. Alright, so let's go ahead and paste that. Okay, so do show IP route. Okay, so now, alright, I'm going to go here. Interface loopback 0 IP address. Okay, do show IP interface brief. Our interface is up. Okay, and we are good. Okay, now I don't have 2.2.2 in my routing table. However, I'm going to put it in the default route. Now, IP route. What is going to be the IP address for default? 0.0.0.0. And what is going to be the subnet mask? 0.0.0.0. Okay? That is how we identify a default route in the actual syntax of our operating system for Cisco iOS. Okay? 0.0. And now, default route without gateway. If not a point-to-point interface, may impact performance. Okay, so I've never seen this before. Okay, but at the same time, what this is saying is this. Okay, and God knows, I've probably seen it 1,000 times. I don't remember. All right, but here's the reality. What it's saying is you have a default route. Your default route should be, from a performance and accuracy perspective, be a point-to-point link. Now, okay, let's say I have router 3 also hooked up that is daisy chained to router 2. Its loopback address is 3.3.3.3. Okay, and if I say my default route, okay, is an IP address of 192.168.3.3, okay, what's going to happen is your routing table is going to have to look up 3.3, okay, all right, and do another lookup because it's not in the routing table. Okay, meaning that it's going to do another lookup and use a default route. All right, to get to that network, meaning that I'm doing two lookups, multiple lookups. Okay, so we want to make sure that our interface here or our IP address is the very next directed connected hop. Okay, all right. That is one of the rules we want to follow. We want to make sure that our interface and first of all, if we're using an interface, we want it to be directly connected, meaning that the only thing on the other side of that interface is only one possible IP address. Okay, or we don't have to use an interface in our routing table. We can use an IP address, but you got to understand now, if I use an IP address, I'm going to have to do a routing lookup to find out what interface it is. So if I put the interface in that command, it's just, you've done a job for the router without having to do an extra lookup in the routing table. Because the bottom line is, it's going to keep doing lookups until it gets to a directly connected interface. Okay? That's how a router works. Alright? So, for performance and efficiency purposes, you want to make sure that your IP address that you're using is your very next hop. For even more efficiency, don't make the routing table do a lookup for that IP address to find out what interface it is. Just tell the router what interface it is. Okay, so an extra lookup in the routing table is not needed. Does that make sense? Okay, so what this is saying is, look, okay, if your fast Ethernet is not a point-to-point link, meaning that the only thing that's on the other side of that interface is one IP address that's directly connected, okay? If that is not a point-to-point interface, all right, this may impact performance, okay? Meaning that, okay, you are using the next hop, several hops down the road. Yes, you can do that. However, your router is going to have to keep looking up until it finds out what interface it's using. It was sending out that interface, but what if your path down there has become broken for whatever reason? Okay, all right. Well, you've created a black hole. Now all your traffic is going out the router. Now the router does not care if the information is not reaching its destination. Once it sends it out that interface, guys, it's done its job. Once again, a separate entity. Okay? It does not monitor to say, okay, did you get there? It does not care. All it cares is information comes in on one interface. Where do I switch that packet to? Which interface? That's all it cares about. Once it's sent out that interface, okay, it's done. Okay? Alright? It doesn't care if it gets there. It does not matter. It's done its job. Its job is a router, and it routed the traffic. Okay? Alright? Does that make sense? Now, okay, so let's finish our demonstration here. Okay, see? Now we have a static and a star. Okay, what does our star mean? Okay, where the hell are you? I can't believe I can't see that. There it is. There it is, right there. Candidate default. Guys, use your legend. Okay? Use it. Okay, now, this is a static route. Okay? The star indicates that it's a default route. Okay? And I actually set the 0.0. Now, think about it. If I set an IP address, again, it would have to look up the IP address to find out what interface is going through. Meaning it has to do another lookup in the routing table. That's two lookups. We only want one. Okay? Because every time we have to look into the routing table, we are utilizing CPU usage. Okay? So if you're doing it five hops down the road, then I'm going to look at what the IP address you use. I'm going to have to do a look up, and then a look up, and then a look up, and then a look up. Does that make sense? Okay? All right, until I get an interface that is going out of. Okay? So now, we have a default route. Now, I am going to ping 2.2.2.2. Okay, and yes, it's going to fail, or I'm sorry. Now let's stop right there. Why didn't it fail? You know what? Matter of fact, let's do it this way. Okay, now, let me get my drawing pad. Blow my nose. My nose is very bad today. Oh my God. Alright, now, let's take a look at this. Okay, when router 1, I was trying to use a pen, but I was not going to use the mouse. Plus the mouse has a scroll button, so. Okay, router 1 is going to ping 2.2.2.2. Now, when it sends out its request, okay, by default, unless you specify a source command, we are going to build the source and destination IP address information based on the interface that was chosen in your command. Okay? Now, if we were using an IP address, we were still going to, and that IP address at the second lookup came down to F800, we're still going to use that interface. Whatever the egress interface is used by default without a source command, that is the IP address we are going to use in our IP headers, okay? In our packet information. These are called headers. I don't know if we discussed that or not, but sorry if that is the case. Okay, so 192.168.1.1 destination IP is 2.2.2.2. Now, in my routing table, do I have 2.2.2.2? No. Okay? But I have a default route. And this is the information that's going to go out and come in to router 2. Now, when router 2 goes to respond, it knows that it needs to flip, okay, the source and destination, making it 2.2.2.2, and the destination is 192.168.1.1. Is this in my routing table? Absolutely. Okay. Actually, you can't see me underlining, but let's try it this way. Okay. There it is. It's there. So it knows, okay, that it needs to go out that interface. Now, most likely it's not going to be 2. It's not going to be 2.2.2.2. Most likely it's going to be 192.168.1.2. Now, how do we know what is going to be? You know why? You know what? I'm going to show you a command that you're going to utilize forever after I show you how to do this. Okay? And this is how we see what is happening in the background of a router. Okay? And it is called debug commands. Now, when you're debugging, okay, you're bringing information to the console. All right? Now, I'm going to say debug IP where are you? There he is. Packet. Okay? And I am going to turn it on. Now, I'm going to ping, but only a repeat of 1, because if we you're going to get the same information 5 times over because you're sending out 5 pings, right? So we only want to see it once. Okay, so now let us, and you know what? Let's do this again. And we're going to say no service timestamp. Okay, to get rid of these, January 2 and times. Okay, which you would never do in production, but um, for studying, we like to get that out of the way. Okay. Now we're going to copy all this output. We're going to paste it. We're going to bring it nice and big. Okay, and we're going to take a look at each one of these messages. Okay, so now a packet is being sent, okay, with 192.168.1.1 as a source. That's what this S is, okay? It's not sent, it's source. And a destination of 2.2.2.2. Going out of Fast Ethernet 00. Okay? The length of this packet is 100. And we are sending. Okay? That means, whenever you see that message, okay, that means that everything has worked perfectly. Okay? We have created our source and destination MAC address and our source and destination IP address. That means everything's working. Your ARP table is properly engaged and is in the actual table. Okay, all that stuff is working fine. Now, this is sending it, but there's another one that gives the same information and says sending full packet. This is the actual sending the packet after it has been put on the wire. Okay? Alright? So good. We've done our job. Okay? Now, I was right. I get a input packet, okay, being sourced from 2.2.2.2. It's coming in on FAO 00, and the destination is 192.168.1.1. Okay? Alright? Great. Alright? Now, this source information coming in on FA00 and destined to our 192.168.1.1 is routed by the RIB. What is the RIB? Okay? Routing information base. Okay? That is the route table, guys. Okay? So even though the packet came in, you understand that we had to still look it up in the routing table to route that traffic to where it needs to go to. Okay? Alright? And it goes in our queue, and now it is received. Now after that, guess what? We stopped the process because we are complete. This is everything that happens when we send a single ping. Okay? Now, let's see what it looks like. Of course, my microphone's like right in the middle. Okay? So let's see what it looks like when I take out the repeat. Yeah. That's kind of difficult to read, right? That's why we do it that way. And the timestamps, okay, taking that out of there makes it easier to read too. Okay, so never do this in production because, as far as the timestamps are concerned, and never do debugs on a on production, okay, unless you're really good and know what the hell you're doing, because I want you to think about something that's doing 1,000 packets per second, and you do this command without being very detailed with what you are typing in, okay, and being very specific. All right, you are going to get so much information coming to the console that it's going to lock you out of the console. You can't type in one bit of information, and now nobody else is going to be able to log into that console. Period. Okay, because once they log in, they're going to get all that information. Meaning you have to physically either reboot the router, Okay, and that has happened too. Or you're gonna have to be slick and paste and hit enter if you are able to do so. The console messages can come in so strong and so much that your keystrokes won't even register. Okay, because their queues, the console queue is so full. All right, you can't get a letter in edgewise. Okay, so this command is for lab. If you're going to do it in production, which I've done 1,000 times, but I know what I'm doing. Okay, do not do this command in production. All right, now with that being said, oops, nope. All right, so now let us go back and bring up my drawing pad again. Okay, and let's go ahead and get rid of, where is my mouse? There it is. All right, we'll go ahead and cut that, get it out of the way. And now, let's talk about split horizon. Okay. Come on, y'all. Let's start this crap. Oh, that's my bad. I need to actually bring this program back up. And you know what? We need to put this on. Let's stop doing this over and over and over. Okay. Router 1 is our main router. Okay. Router 2. Router 3. Alright. Now. This is our logical interface, but not our physical. Okay? Our physical goes like this. These routers are using the internet to connect to router 1. Okay? So router 2, in order for it to communicate with router 3, all right, so 3.3.3.3, this line with a slash simulates a broadcast domain or a network, okay? So that's how we draw it. So anytime you see that, you know we are talking about a network, all right, that's coming off the router. Okay, and we have a 192.168.5.0 network, okay, /24. All right, that's how we draw it. Okay, so now, router 2, in order to communicate, because we have these logical connections, and router 1 is our headquarters, okay? So now, our headquarters, come on, really? Okay, our headquarters, okay, router 1 is all the routers, all the site routers, I don't care if you have 4 or 5 or 6 sites, all connect to router 1. So in order for router 2 to communicate with router 3's network, okay, when it goes to ping 3.3.3.3, it needs to go up to router 1, okay, as the first hop. Then router 1's going to look up the routing table for 3.3.3.3 and send it down to router 3. Now, here's the thing. A packet came in, okay, on FA00, okay, and here's the thing. Remember what a router does. Packet comes in, and it makes a decision to switch the packet out to another interface. But in this scenario, router 1 has to send the packet out the same interface in order to get to router 3. Okay? Now, by default, split horizon is enabled. And if we set this up like this, okay, the packet will never get to router 3, okay, because split horizon is enabled. We have to say no split horizon on the command of this interface, and then that traffic will come in. Okay, not to mention the fact that if split horizon is enabled from a routing protocol perspective, okay, router 2 will never even learn this in the routing table as far as a dynamic learning, because that's what routing protocols do. They go out, they share information, and they dynamically learn routes. Okay, yeah, that's a lot better than actually statically putting them on every interface, right? I mean, every router, right? Okay, that's the beauty of a routing protocol, to dynamically learn routes. But because split horizon, okay, is enabled by default for particular protocols, router 3 or 3.3.3 will never be learned on router 2. Okay, so you got two aspects of that. The dynamic learning of a route will not work, and the forwarding of traffic will not work. So we have to say no split horizon on FAO00, and magically 3.3.3.3 will come onto router 2's interface. And that's what split horizon is. Okay? Alright? Let's go ahead and close this. Okay, now let's talk about encapsulation. Okay, encapsulation is the concept of... Okay, let's go back over here. Alright, look. I gotta bring it back up. Yeah, much better. Okay, so remember, we have our source MAC and our destination MAC. We need this, okay? We have our source IP and destination IP, okay? We have port number, all right, 1055, okay? So now, we have these attributes, okay? Now, our MAC address, where does it sit on? At what level? Okay, this will be layer 2. The IP addresses, layer 3. The port numbers, layer 4. So you got to look at the concept now. We have our data. Okay. All right, over top that data, okay, we're going to have our layer 4 information. Okay. On top of that, we're going to have our layer 3 information. On top of that, we're going to have our layer 2 information. And as long as we have layer 2 and layer 3 in completion, okay, our encapsulation is successful. If we're missing an entry in the ARP table at layer 2, you're going to get a message in your debug message of IP packet saying encapsulation failed. Okay? Meaning that the packet ain't getting sent because we can't encapsulate it. Every one of these little boxes that are attached on top of each other, okay, all right, and we're saying on top, okay, because think of it as an envelope. Here's your data, okay, this data goes into this envelope, this goes into this envelope, and this goes into this envelope. So when an ingress packet, okay, coming in our interface, the first thing we look at is the layer 2 information. All right, we look at that information and says, is the destination MAC address for my interface? And it is. So now we open up the envelope, toss that, and look at the layer 3 information. Is the destination IP address going to me? Yes. So now we open up the envelope, okay, and look at the layer 4 information. Am I listening on port 1055? Yes. Open up the envelope, throw it out of the way, and take this data now, okay, that has been encapsulated with layer 4, encapsulated with layer 3, and encapsulated with layer 2, okay, and take that data and send it to the application that is listening on 1055. Okay, now from a Wireshark perspective, your layer 2 is going to be up here, your layer 3, and your layer 4, okay, which you're going to have to uncollapse each one of these, look at the information, okay, and layer 2 is going to be at the top, okay. This information is encapsulated with layer 3, and layer 3 information is encapsulated with layer 2, and that is when encapsulation is complete, and that is when the network card will send out the data. Okay? Now, with every protocol, okay, we're using TCP/IP to communicate back and forth, alright? Okay? Ping is an application that is a part of the TCP/IP protocol suite. Okay, we call it a suite because it's a collection of things that comes with TCP/IP protocol. Now, here's the thing. We need to use, in order for our layer 2 encapsulation of the interface from router 1 to router 2, this needs to be the same language. Okay? A protocol literally states, okay, we're not talking about military protocol, but it's the same thing, right? It's a set of rules, okay, that must be applied, whether it is a proprietary, all right, I'm spelling that wrong, or a industry standard. Okay, if it's an industry standard, that means you have to follow the standard of that protocol in order for communication to happen. If you decide that you're going to code it the way you want to, guess what? You have now made a proprietary protocol. Now, Cisco uses its proprietary protocol, and it works just fine. But we could change that to a point-to-point protocol. Okay? Alright? As long as this interface and this interface is configured for point-to-point protocol, PPP, they can communicate. But if we use HLDC, okay, or HDLC, I can't remember. Alright, which we're going to look at in a minute. Alright, that's Cisco proprietary, and as long as they both have the same protocol on each one of these, they can communicate just fine. Okay? Alright? Now, anybody can do this. Create their own protocol. Okay? Cisco does it with Cisco Discovery Protocol. Okay? What would be the industry standard for learning devices in your network? LLD, Link Layer Discovery. Okay? Alright, now, your HDLC, okay, high level. God, I hate when it does that. Alright, let me take this pad away, because we're in Notepad, and whatever I'm drawing, apparently it wants to write it. Okay, so now, link high level data link protocol. Now, notice I said layer 2 protocol for encapsulation. Okay, alright, data link is your layer 2. That's what we call it, the data link layer. Okay, so at layer 2, HDLC by default is what Cisco uses for encapsulation. Okay, so the way it encapsulates all the information before it's sent out the interface, that's the job of HDLC. Okay, and as long as the other side of the link is running HDLC, it will be able to receive that information. If I have point-to-point protocol on one side and HDLC on the other side, what happens? The protocol for that interface goes down. Okay? So, let's take a look. Come on, get out of my way. I think it might be IP command. Are you serious? I'm gonna have to look this command up. It won't be the first or the last time. I thought it was encapsulation. Why is it not there? Enter interface mode. Oh. Is it? No, it's just encapsulation. It's not enable. Alright, okay, so it's not there. Wow. Okay. Well, scratch that. We're not going to be able to test that, and that is probably because of the iOS version that we have on there. I doubt if it's the platform. I think it's the iOS issue, that particular version. Now, let's make sure this is enterprise version and not IP services. Do show version. Yeah, this is advanced enterprise. It should be there. Okay. Oh well. It's not, so we can't test that, but still, nonetheless. Okay. HDLC is Cisco proprietary. Okay. And you gotta understand that this particular protocol is what organizes the data into a frame, which will be the collection of the layer 2, layer 3, layer 4 information. Okay, put it all together, it's called a frame. That's why in layer 2, okay, we call the data frames, and at layer 3 we call them packets. They are a difference, but okay, from a teaching perspective, frames and packets are the same thing. Okay, so don't get it twisted, don't make it overcomplicated. Alright? Okay. PPP is an industry standard. Okay, this allows compression. Okay, obviously it uses the CPU process, which I don't think that HDLC does not use CPU process, but do your own research. Okay, cool thing about this is multi-link. Multi-link allows me to create a logical interface like a loopback, give it a number, okay, and add multiple links underneath that particular interface. So, if I create multi-link interface named multi-link 1, alright, I can put 4 interfaces in there, okay, and give multi-link 1 an IP address, okay, and the cool thing about it is on the other side, okay, obviously I'm going to have 4 links as well, and I will be able to utilize 4 links, okay, with under an umbrella of one logical link. And the multi-link, number 1, will be the one that's doing the forwarding, but from a logical perspective, that forwarding comes down from the multi-link onto the physical interfaces underneath the multi-link. Okay? But from a routing perspective, in the routing table, you're going to see that this particular network needs to go out multi-link 1. Okay, it's pretty cool. All right. It also allows authentication on the link, which is cool as hell. Okay. All right, and then I can use PAP and CHAP for that stuff, and something we're not going to be learning anytime soon. Okay, so that. All right, and that is the conclusion of that aspect. And I had a lot of fun. I hope you did too. And be strong, be determined, be Cisco, and I will see you guys on the next one. Okay, so I just started to render and then I stopped it because something came to my mind just as I hit that. Okay, this encapsulation is not a fast Ethernet technology, but a serial one. Do show IP interface brief. Okay. So interface serial 10 encapsulation. There we go. HDLC and point to point. Okay. So this is for serial links, not technology for fast Ethernets. I don't know if they could do that now with a newer iOS or a newer platform. I just know that that's what popped in my head. Sorry about that, but this is not an iOS or platform issue. It's a interface type scenario. Okay, and that was it.